In this video, we're going to talk about Fermi-Dirac distribution function, which is given by f of e is equal to 1 over 1 plus e power e minus ef over kt, where e is the energy level, ef is the Fermi energy level, T is the temperature, and K is Boltzmann constant. And the particles which obey this Fermi-Dirac distribution function are called fermions, and electrons fall under that category. So that's why we are discussing this particular topic in this course, because electrons follow this distribution function. So what does this f of e means? So let's say if we have this energy level, and if we substitute e into this f of e function, f of e would give us basically the probability of an electron filling this energy level. Because it gives probability, so the value of f of e would always lie in between 0 and 1. So now let us try to plot this function f of e. In order to do that, we need to know the values of the temperature T and EF. So we can assume the temperature. So I'm taking the temperature to be 0 Kelvin to start with. And EF, so we're not going to assume any value for EF. Instead, we'll talk about the energy level E with respect to EF. So at T equals to 0 Kelvin, let us find out for E greater than EF. Let me take this to be the first case, where the f of E value would be 1 over 1 plus. As E is greater than EF, exponential, it will be positive, over kt, where t is 0, so here 0, which would be equal to 1 over 1 plus e power plus infinity, which would be equal to 0, which tells us that the probability of finding electrons above the Fermi energy level is 0 at t equal to 0 Kelvin. Now let us see for the second case where E is less than EF, where we'll have 1 over 1 plus e power, the numerator here, which is E minus EF, where E is less than EF, so E minus EF would be negative, over KT, where T is 0, so we have 0, which is given by 1 over 1 plus e power minus infinity. This would be equal to 1. So now it says that below Fermi energy level, the probability of finding electron is 1. Let us try to plot these values in a graph, where we are taking E, the energy level in y-axis, and f of E on x-axis. Now let me assume EF is somewhere here, because we are talking about E with respect to EF, and we know that f of E values will be between 0 and 1. For t equals to 0, the f of E value for E greater than EF is 0, and for E less than EF, which is below EF, the probability is 1, which means the f of E value is 1. So this graph that we have plotted here is for T is equal to 0 Kelvin. So in order to have a comparison, let me plot two more graphs, one for T equals to 300 Kelvin, which is room temperature, and another one which is above room temperature. Let's say that is T equals to T1. This graph is for T equals to 300 Kelvin, and this graph is for T equals to some T1 Kelvin, where 0 Kelvin is less than 300 Kelvin, less than T1 Kelvin. Now let us see what is happening when temperature is increasing to this Fermi-Dirac distribution function. So I'm taking, let's say, some energy level just above the Fermi energy level. Let's say this is E1, at which point for T equals to 0 Kelvin, we clearly know the probability of finding an electron is 0. And for the second case where T is equal to 300 Kelvin, the probability of finding an electron at that energy level is some finite value, let's say, which is P1. And for the third one, the probability of finding is, let's say, P2. Now we can say that 0 is less than P1 is less than P2. Now this is for corresponding 0 Kelvin, 300 Kelvin, and this is for T1 Kelvin. And we know T1 Kelvin is greater than 300 Kelvin and 300 Kelvin greater than 0 Kelvin. We are seeing here for this energy level, the probability of finding an electron at this energy level increases as temperature increases. And similarly, if we take another energy level just somewhere below the Fermi energy level, let me call this to be, let's say, E1 prime. In this case, the probability of finding an electron at T equals to 0 Kelvin for this energy level is 1. And similarly, at this energy level, for 300 Kelvin, let's say it is P1 prime. And for this third graph, it is, let's say, P2 prime. We can say the relationship for them as P2 prime is less than P1 prime less than 1. And this is in the order of T1 Kelvin greater than 300 Kelvin greater than 0 Kelvin. Now here we can say that as temperature is increasing, the probability of finding an electron is basically decreasing. And we can understand this probability decreasing below the Fermi energy level and probability increasing above Fermi energy level as temperature is increasing based on our understanding of semiconductors with respect to temperature. We can say as temperature increases, the silicon bonds break and there will be more electrons in the conduction band, which means at higher energy level you will find more electrons compared to less temperature. So that's why we are seeing as temperature increases at E1 energy level here, the probability of finding an electron is basically increasing. Whereas below the Fermi energy level, let's say similarly you can see the number of electrons in valence band decrease because the electrons actually go to conduction band. So we can say the number of electrons or probability of electrons at lower energy level decreases as temperature increases, because these are basically going to higher energy level. So that's what the Fermi-Dirac distribution function tells us. We have simply specified what is EF. We said this is Fermi energy level, but now let us see what it actually means. So at Fermi energy level, all the graphs, different temperature graphs, meet at one point, and if we project it over to f of E axis, we get a value exactly 0.5. So based on this, we can define what Fermi energy level means. So we can say Fermi energy level is the energy level at which the probability of finding an electron is exactly half, or we can say it is exactly 0.5. Or in other ways, we can say the probability of finding an electron is equal to the probability of not finding an electron. So that energy level is the Fermi energy level, which is EF.